Hello. This element right here, element 66, is dysprosium. Its Greek word means dysprositos, which translates into English as hard to get at. I'll explain why it's hard to get at in a bit. Dysprosium was discovered in 1886 by a French chemist named Lecoq. Sorry I cannot pronounce any French, so I'll spell it for you. Lecoq. And he discovered it accidentally when he was researching yttrium oxide, in which he subsequently discovered yttrium, erbium, holmium, and dysprosium. It was not until 1950 that Frank Spedding at Iowa State University isolated dysprosium as a pure metal using ion exchange chromatography. Now, you might be wondering what ion exchange chromatography is. Well, in its simplest description, it's the separations of ions and polar charges based on their charge. Now, dysprosium can be separated using liquid-to-liquid exchange technology, which separates atoms and particles based on their solubility. Now, since I've been discussing about dysprosium, you might be wondering where in the periodic table is this interesting element. Well, it's right here. As I clearly mentioned at the beginning of the episode, element 66, but more specifically on group 3, period 6, and is classified in the lanthanides, while having an oxidation number of 2, 3, or 4. Be specific with its oxidation number. It is a positive oxidation numbers for both 2, 3, and 4, since dysprosium wants to give away its valence electrons of 2, 3, or 4. Since I just mentioned lanthanides, and you might be wondering, what in the world are these classifications of elements? Well, I got the answer for you. Lanthanides are classified next to the transition metals on the periodic table, but form a separate group due to their difference in electron orientation, since instead of the other elements on the main periodic table, lanthanides do not increase their electron shells on their outer valence shell, but instead increase their electrons in their inner shells, which is the opposite of what the other main elements use. The most abundant form of dysprosium, dysprosium 126, has 66 electrons, 66 protons, and 96 neutrons. It's abundant in 25.475% in the Earth's crust. Now, since you keep hearing the words 666, you might consider dysprosium to be the element of the devil. No, it's not that. Just don't. It's not an element of the devil. No, that's just sulfur. There is only one main isotope of dysprosium that's radioactive, dysprosium 154, with a half-life of 3 million years, and decays through an alpha decay, which it emits a helium atom. And alpha decay is the largest form of radiation and can be easily stopped with a piece of cloth. Though there have been other radioactive isotopes of dysprosium, mainly those generated in particle accelerators, in which they ram subatomic particles or atoms into each other. Pure dysprosium metal is not naturally occurring and cannot be found on this Earth, and can only be created through man-made designs. Since dysprosium has an oxidation number of 2, 3, or 4, let's focus on the 2 right now. That means dysprosium wants to get rid of 2 valence electrons, and since oxygen element 8 wants to have 2 electrons, you can commonly find dysprosium oxide bonded together. Another way of finding dysprosium in a naturally occurring compound is in Himalayan sea salt. Right here, where you can find traces of dysprosium in the Himalayan sea salt abundant elements. Right here, Himalayan sea salt has a large quantity of elements found on the periodic table. There's just too many to list right now. If you're curious in finding what elements are in Himalayan sea salt, you can always Google it. Though you can get pure dysprosium metal, there's not a lot of practical uses for dysprosium, since A, it oxidizes quickly with the air, since I previously mentioned dysprosium oxide, and B, it reacts explosively with water, relating to that of the alkali earth metals, which I previously mentioned its oxidation 2 number on the periodic table, and which the alkali earth metals also have an oxidation number of 2. And also for clarification, the oxidation number 2 is a 2 plus, not a 2 negative. 2 plus, and in which they want to give away 2 electrons. Though since there's not a lot of uses for dysprosium as a pure metal, you will always find dysprosium in commercial use as alloys. Now, as I previously mentioned in the beginning, dysprosium's name, dysprositos, meaning hard to get at, is meant in today's terms as dysprosium, is really hard to separate as it's very similar chemically to a lot of the lanthanide metals, so the separation process is really hard. And it's really hard to get at since there's not a lot of commercial uses for dysprosium. But soon, I will list some of the uses for dysprosium. Dysprosium is used in neodymium iron-boron magnets, since its property is very useful as it resists demagnetation at high temperatures, which makes it ideal to use in their motors, which often reach high temperatures, and is often used in motors for wind turbines. And the demand for dysprosium has increased as the demand for wind turbines has increased. Another use for dysprosium is in dysprosium oxide nickel, where it is used as control rods in nuclear reactors, as it does not swell or contract when it absorbs large amounts of neutrons over extended periods of time. Dysprosium's last main commercial use is it is used in conjunction with vanadium for lasers. Finally, dysprosium has little to no biological effects on humans, but it is toxic in soluble salt form only if consumed 500 grams, but in insoluble form it is non-toxic. I would like to give a shout out to the Royal Society of Chemistry for its fun and educational interactive periodic table, which can be found online and on the App Store, and also to Theodore Gray, the writer and author of The Elements, a visual exploration of every known atom in the universe, which has been a childhood favorite for me as it describes every element in the periodic table in a fun and eccentric way while maintaining its educational purpose.